I read problem 9 this morning before going to tennis training, and my first instinct was, how on earth could I be able to prove that? That's problem A. But then I remembered that there was some information at the beginning, so we'll just have a time try to see what's happening, what it says here. So we have this map on the elliptic curve, and it says it's an automorphism. So that means adding 2 points, then either using it before or after should result in the same point. Obviously, minus p is mapped to minus p. That's just changing the sign of y. So I'd like to have this maps a line in the projective space to a line, another line. So 3 points lying on a line, their images will also line the line. And that actually shows that it is a homomorphism, and of course it's 1-to-1, so it's an automorphism. So check there. The next step, and that actually means something if it contains a square root of -1, of course, and now so if we have 2 points, x point y1 and minus x point y2, then k will contain a square root of -1. So only one of these points exist. And since it's an automorphism, they must have the same order. This may come in handy here. That was the first information. The next is the action of the Galois group of the algebraic closure of k over k on the coordinates of the point in an algebraic closure. Oh yes. So let's go to A. L is an odd prime, have elliptic curve, as at most L FQ points on the projective curve. We have L squared points of order L, and in K there may be fewer, because the polynomial determining for solving points of order L may have reduced degree, because some of the high coefficients may map to naught in FQ. And so we have at most I'll just denote a bar to say algebraic closure. So this bar means algebraic closure. And when q equals 3, there is no square root 1 in fq. If we have one point of order L, let's call it P, since it's odd, NP for n equals 1, 2, up to L minus 1. Those points will have order L as well. And then, of course, unity point at infinity comes in to give the L. So if there's one point, there are L. And if there is another one, then I claim that all of these points make up L squared, but that was impossible. Oh, now what am I saying? Oh yes, because if we have one point, x point y, say that's the guy, then the one mapped by here, if it exists, and which it doesn't, yeah, none of these points may be equal, so that gives L squared points of order L. And if we take one of them, say P, and then use this automorphism, which we'll call, what do we call an automorphism? Phi? Isn't that the conventional? Then phi of P is a point of order L as well, and it will lie in the algebraic closure. But it cannot lie in K, the elliptic curve of K itself, because K does not contain a square root of minus 1. So that was the first guy. That was the first line. Next, there are at most 8 points of order 4. We have, of course, the 4 points of order 2, so there are 12 left. I guess the same argument holds for points of order 4. There are at most 16. And we know there are 4 of order 2, so that means 12 of exact order. Still at most. And when we apply this guy, now, if we have 1 point of order 4, we use the same argument as before, and this is exact order 4, then P, 2P, 3P have exact order 4 as well. And if there is one other, this is lie, that's order 2. Sorry. Which is neither P nor 3P. Then we have P, 3P, Q, 3Q, P plus Q, P plus 3Q, 3P plus Q, and 3P plus 3Q. Do we, or am I wrong here? If we, this is obvious, 2 points of order 4. They're all distinct, obviously, and they trivially have order 4, 1, 2, 3, 4, 5, 6, 7, 8. That gives 8 points. Oh, when there are 8 points, then there are more than 6, and that means that 2 of them will be connected by this orthomorphism phi. 2 of them must, at least actually, 2 pairs must be connected by this guy, which implies that -1 lies in K. So that's impossible. Thus there are only these guys. So we have P and 3P, and then we have the 3 points of order 2. etc. That gives 8 altogether. So that I don't think any of them can be equal, so if there exists one of exact order 4, then there are 8. That solves A. All right. I didn't think I would be able to do it. I'm very pleased that I was able to get through it. I don't hope I've fucked up anywhere. All right. So let's give B a shot. A group of FQ points of a group of order 2. The group of FQ points is the product of a group of order 2 and a cyclic group of order Q plus 2 half. Well, if there's no point of order 4, then we of course have the 4 points of order 2, but one of them can come in order 2, and then the other order 2 will come in the cyclic group, which has an even number of points. All right. So we will need to show that these points form a cyclic group. I'm just trying to multiply this with all numbers from 1 to 3. 3p plus q, that's this guy, that means we should be able to write the elements of order 4 as one of the elements of order 2, let's say 2p, group generated by 2p, plus the group, and that's a direct sum, isn't it, of p plus 3q. I better write them all up. There are 8 there. I'll do that on the next page. We have p plus q. Let's be systematic. First, naught times this. And 6p plus 2q. And then 3, that's p plus 3q. Then we add 2p to these guys. That's p plus q, p plus 2q, no, just 2q, and 3p plus 3q, and then we add 2p again. Oh, that's the same. So we have 1, 2, 3, 4, 5, 6, 7, 8 elements. Could any of them be the same? 2p can't be any of these. No, can't be 2q, because then p would be... Oh, it's actually possible that p and q end up the same place. No, it's not. Oh yeah, they... So my problem is, how many original points are there to one point? And we had that at some time, and I think it's 4. When we double, there are 4 points. And as far as I remember, that came from the doubling of points in the basic lattice. Let's this be the basic lattice, and then when we double, we end up in the double here. And if we want to end in some specific point, say we want to end here, then we may as well end here, here, and here. And the original points we get from that, that's this guy, this guy, this guy, and this guy. So we have 4 original points. So there are 4 points giving 2q when doubled. One of them is q, of course. Let's do it the other way around. If we have now watch this. Oh yeah, 2p. I just forgot what I was doing. This was the impossible situation. So we have the 4 points of order 2, and then only 2 points of order exact 4. Therefore, we shouldn't be using that point. So there are no other point, and the point P gives us 2 points right. I try again. Let's forget all this. We try again. We have 4 points of order 2 and 1 point of order 4, which gives 2, of course, and then p squared can only be one of these guys, so we choose another one. Let's say it's equal to u1, then we just take u2 plus p, the group generated by this. And I think it's obvious that it contains 4 elements and 2 elements, so altogether it's 8 elements, and now we are home. So that was the first problem, that the the elements of order 2, they can be taken out as an element of order 2 and an element of order 4 in this group, or an element of order 2, which there must be. Okay, next, we actually know there are exactly q plus 1 elements in the elliptic. I had an idea, and that is if it's generated by elements, distinct elements of prime, so we have En of k slash the units. This is the group of units, not units of elements of order 2. If it's generated by elements of distinct order, distinct prime order. Now, what shall we call it? P1 or Pi order Li being a prime. I claim we should just take one unit. Oh, let's take all of order 4, by the way, all of order 4. Whatever the last be. That was my idea. Let's see if that holds. I have a feeling it will require proof by induction on the number of addends. For one, it's true, trivially. So it's true for one group, and we add another guy with a distinct prime order. Then if we have a generator for P1 plus a generator for the other one, say G2, and then we just multiply x is a bad number with I and k, naught to 1 to the order of P1 and j 1 to L2, the order of G. Then I claim that we get J times L distinct elements. Isn't that obvious? Otherwise, by subtracting, if there are two which are equal, then one of these guys must vanish, which is impossible, because G2 doesn't lie in, that's not the point really. Oh yeah, this is one that doesn't lie in the group generated by P1. Please. This element does not lie in this group, so it cannot be equal to an integer times G1. Yeah. That's standard number theory. So that's right. And it even holds if they are mutually prime. Now, I think there was something I didn't show that needed to be shown to do this. We have elements of various orders, at least at most of order. Actually, I think it holds for prime powers as well. Has the feel of the Chinese remainder theorem, really, we're using. Oh, I need to make a generator. It should be a cyclic group, not just a group. So the point is that I want to show that G1 plus G2 is a generator. And that even holds for prime powers, so that's just the Chinese remainder theorem that we need to use to do that. So it's actually simple. So there's just the question of the points of order 2. The units are not, but if we take one of the units out, then the other points of order 4, if they exist, or of order 2, comes into this group. So let's say it's a point of order 4. That's the only special one. Otherwise, we take all the odd orders. So that was the point of order 4, if it is, or another unit. And then just all the points we have here. Point K. And then this guy is simply generated by P plus P1 up to plus Pk. I believe that solves the problem. And having had a break, I think of 3 weeks from mathematics, I'm very surprised if it's true that I was able to handle this problem in one go.